Welcome back. Section 4.8 Coordinates and Isomorphisms. Coordinates. Let V be an n-dimensional vector space with basis S. That is, S will have n vectors. You know that every n-dimensional vector space, every basis will contain n vectors. In particular, you have fixed a basis with n vectors. Let those vectors be v1 through vn. Now fix an order among the vectors of S. Once you fix an order, it is called an ordered basis. What does that mean? You have fixed v1 should come before v2 and so on. Look at this set S2. I have placed v2 first and v1 next. As far as sets go, they are the same set. In a set, order does not matter. So writing one vector first, the other second, or vice versa does not change the set. As a set, S1 equals S2. But as ordered bases, this order is different from this order, so they are not equal. So I hope you understand the distinction between being a set and an ordered basis. Ordered basis means order matters. In a set, order does not matter. So, start with the ordered basis with an ordered basis of V, V1 through Vn. Take any vector from V. We know that V can be written as a linear combination of vectors from S in a unique fashion. You see, S is the basis. S is a basis. So every vector V from capital V can be written as a linear combination from V1 through Vn. Moreover, being a basis doesn't also means not only do these vectors span V, they are linearly independent. A consequence of that is that this expression of V in terms of these vectors is unique. Now, if you have forgotten why it is unique, go back to the lesson 4.6. We have proved that it has to be unique. That is, there are unique scalars a1 through an such that vector V is a1 v1 plus a2 v2 all the way to an vn. So, consider the column made of these coefficients, unique coefficients, for each vector V. You denote it by box V sub S because you are referring to this particular ordered basis of this vector. That column vector is called the coordinate vector of V with respect to the ordered basis S. You see, this is a big phrase. All that is mentioned in here. Coordinate vector of V with respect to the ordered basis S is this. Okay, where do these numbers a1 through an come from? They come from the way V is expressed as a linear combination. The entries of V, box V sub S, are called the coordinates of V with respect to X. So this column is called coordinate vector. Every entry is a coordinate of V with respect to S. Here is an example. Consider the set S1 consisting of 1 and T of P1. What is P1? If you recall, P1 is the vector space of all those polynomials of degree 1 or less. So that's a constant polynomial. That's a polynomial of degree 1. Take these two. This is actually standard basis. Order it. 1 first, T next. Then consider the polynomial. I'm calling it vector because P1 is a vector space. Consider the polynomial 3t plus 5. 3t plus 5. Order matters. 1 is first. So 5 times 1. T is next. 3 times t. So 3t plus 5 is nothing but 5 times 1 plus 3 times 5. In other words, in terms of this particular ordered basis, the vector 3t plus 5, the coordinate vector of 3t plus 5 with respect to this S1 is 5 first, 3 next. On the other hand, consider the ordered basis T1, that is interchange T and 1. In this case, 3t plus 5 is 3 times t plus 5 times 1. Now the coordinate vector is 3 first and 5 next, because you see t first, 1 next. So you see the coordinate vectors very much depend on the order of your basis. Well, what if you have an entirely different basis? S3 is the basis of P1 consisting of two vectors, t plus 1, t minus 1. You may check that this is indeed a basis. Now write the same 3t plus 5 as a linear combination of these two vectors. You can check 4 times t plus 1 plus negative 1 times t minus 1. 4t minus t is 3t. 4 plus 1 is 5. So that is indeed the linear combination. So in terms of this ordered basis, your coordinate vector is 4 comma negative 1. All right. Consider the vector space R3. So R super 3 is the set of column vectors with 3 entries. Let S be the set consisting of v1, v2, v3 in order. So that's an ordered basis where v1 is 1, 1, 0, 2, 0, 1, 0, 1, 2. You can check that these are linearly independent and that they span all of R3. We did set checking in our previous lesson. So that is an ordered basis. Consider some vector v, 4, negative 2, 3. You want to find the coordinate vector of this v in terms of this S. Well, we are going to write v as a1 v1 plus a2 v2 plus a3 v3, and our goal is to find a1 a2 a3. That is, this vector is a1 times 1, 1, 0 plus a2 2, 0, 1 plus a3 0, 1, 2. So 4 is a1 plus 2a2 and no a3. Negative 2 is a1, no a2 plus a3. 3, no a1, a2 plus 2a3. All right, so that is 4, negative 2, 3. You have written that this equation in form of a linear system. Once you have a linear system, you can simply write the augmented matrix. So if you remember, the augmented matrix, when you use vectors, turns out to be just these for the coefficient matrices and the answer vector for the right hand side. Well, what do we do with an augmented matrix? We use elementary row operations to transform the matrix to row echelon form and identify a1, a2, a3. I'm interchanging row 1 and row 2. It is not really necessary, but I do this so that I get not only the 1 above, also the 0 above. Okay, we do that and now get a 0 in this location. Negative row 1 plus row 2. I got a 0 there, no change here, something, something. Now I want a 1 here, so I'm interchanging row 3 and row 2. I got a 1 there. Now I want a 0 below. Negative 2 row 2 plus row 3 is the new row 3. You get a 0 below. I want a 1 here, so divide row 3 by negative 4. This is your row echelon form. This gives us the following equations. First, a3 is 0. Second, A2 plus 2A3 is 3. So since A3 is 0, that goes away. A2 is 3. And then A1 plus A3 is negative 2. But A3 is 0, so A1 is negative 2. Okay. So you found solution for 4, negative 2, 3. A1 is negative 2, A2 is 3, and A3 is 0. So this linear combination gets you this vector. That is, this vector in terms of this basis, the coordinate vector of this guy is negative 2, 3, 0. You see, which is very different from the vector you began with. So coordinate vector is something unique, very much dependent on the basis you choose and the order of the basis vectors. An important consequence of coordinate vectors: suppose S is V1 through Vn is an ordered basis of V. Suppose you take any two vectors V and W. If V is equal to W, that is, you have the same vector repeated, then its coordinate vectors are equal. On the other hand, if the coordinate vectors are equal, then what? Then you know that V is A1 V1 plus A2 V2 plus AN Vn, which is also W, because W has the same coordinate vectors. So W's expression would be the same as V's expression, so they are actually equal vectors. So notice this is very important. V equals W automatically implies the coordinate vectors are equal. On the flip side, coordinate vectors equals also imply V equals W. So that is, once we fix an ordered basis of a vector space, any vector can be uniquely identified by its coordinates. So once you know the coordinates, you know the vector. For instance, recall the vector space P1 with ordered basis S equals 1t. Any polynomial in P1 can be written as A0 times 1 plus A1 times t. So A0, A1 are the coordinates of that polynomial. So you may write it as a point in R2. That is, we think of the x-axis as the constant coefficient and y-axis as the t coefficient, coefficient of t. All right, so a point in R2 will give you a polynomial of degree 1 or less, and a polynomial in degree 1 or less will give you a point in R2. Okay, so suppose V with its own O plus and own O dot, and W with its own O plus and its own O dot be two vector spaces. Okay, they are both real vector spaces. A bijective function L from V to W is called an isomorphism of V onto W. Bijective, if you remember from, I don't know, pre-calculus, bijective means you have to be one-to-one and onto. In other words, bijective, you have to be injective and surjective. Injective is one-to-one, surjective is onto. So a bijective function that is both one-to-one and onto, it is called an isomorphism if L of, you take two vectors V1 and V2, L of V1 O plus V V2 is L of V1 O plus W. So notice L takes a vector from V to a vector in W. So LV1 is in W, LV2 is in W. So when you add these two vectors, you are using the vector addition of W, because these two vectors now, L of V1 and L of V2 are in W, whereas V1 and V2 are in V. So these two vectors are added using vector addition in V. Likewise, L of R O dot V So this O dot is the V, R O dot W L V. Okay, let's continue in the next video.